Okay, class. So we just started the Newton's law of viscosity, right? And just to remind you very quickly what we did. So Newton said that the shear stress applied on a fluid is proportional to the velocity gradient, right? And we said that with proportional sign, we can just identify the characteristics, but we can't quantify anything. So we need to quantify and we need to remove the proportional sign. So what we did using a constant, we said that is the Newton's law of viscosity. And what is the name of that mu? Here, what is the name of that? This one is called viscosity, like the mu, and it represents the viscosity of the fluid, right? Represents the resistance the fluid can experience. Okay, so this is actually the equation. Now, based on that, like based on these characteristics, or the relation between shear stress and the velocity gradient, we can classify the fluid into two parts. And one more thing, we don't have any new class lecture today. You can use your class lecture 5 because we didn't complete that in our last class. Okay, now based on the relation between shear stress and velocity gradient, we can classify the liquid into, sorry, the fluid into two parts. One is Newtonian fluid, another one is non-Newtonian fluid. Now, to explain that, can I consider this one as the y and this thing as x and develop a plot here? This one. Now, if that viscosity or mu doesn't change with applied pressure or applied stress, if it is constant all the time, like y equals to mx, what will be the shape if I draw a line within this plot? It will, if it will be linear, right? Something like that, right? And what will be the slope of that line? Mu. So basically, this will act as y equals to mx, the straight line equation, right? Now, if any fluid shows this type of behavior, like no matter what amount of shear stress you are applying, like this one, no matter what shear force you are applying, it is always the mu. This type of fluid is called the Newtonian fluid. Okay, in your class lecture, there should be some blank spaces. You can write on that blank spaces. That means whenever the viscosity is same, no matter what amount of force you are applying, it is called non-Newtonian fluid. Can you give me one example of Newtonian fluid? Can you give me one example of Newtonian fluid? Water. Yes. Another one from gas. What can be another example of Newtonian fluid? Air. Because if you just think about applying force on a water volume, that will not change the viscosity, right? It will be same. So that means it will be always same no matter what force you are applying. And that's why the water, air, or oil, those are just the Newtonian fluid. Okay. So you should have one plot where we have multiple fluid examples. Here, do you have that on your copy? This one? Are you done with the previous slide? Or okay. So since this one is the viscosity, and the more viscous it is, the more slope it will have, right? Now, from this picture, can you tell me which fluid is the more viscous fluid? Is it crude oil or the air? Which one is the more viscous here? Crude oil, because the slope of crude oil is highest, right? And what is the lowest viscous fluid here? So just by looking at relative flow, can we tell which one is more viscous and which one is less viscous from this point? Okay, good. Now, here you can see all the lines, they are linear, straight, right? Straight line equation. Now, the example you just saw in the lab, do you think the viscosity is always same no matter what force you are applying, or it's different? It's different, right? Because when we applied extra force, it was acting like a solid. I couldn't insert my finger there, right? But when I didn't apply too much force, it was like slowly my finger was going inside of that fluid, right? So this type of behavior, when the viscosity is not constant with shear stress, that is called what? What type of fluid is that? Non-Newtonian. So these two types should be non-Newtonian. So all the lines you are seeing here, like this is nothing. It's just by mistake it's appearing on the screen. So these two, those are the non-Newtonian. And if you want to define the non-Newtonian, they will have a non-linear behavior between applied shear stress and shear strain rate, right? Now, I added two videos, a video link here, which you have on your copy, but those are basically what we just saw in the lab. Like you can jump on water construct solution. One video is about that. If you're interested, you can watch that video. Now, I will discuss in details about two types of non-Newtonian fluid. One is dilatant, another one is pseudoplastic fluid, which I will do in next slide. If you're done with this slide, just let me know. Everyone's done with this slide? Okay, I will wait a few more seconds. Everyone's good with this slide? Okay. So for this one, you will give me some arbitrary number, like just arbitrary number. I will just draw two slope here. And this one is 1 mu, this one is 1 mu here. Okay, give me any number here, any number for this one. 5, okay. This is just arbitrary number, 5. Now, what do you think here? The slope of this point, is it greater than 5 or less than 5? It will be greater than 5, right? Because we are seeing it's like steep. So I will use 10 maybe, just arbitrary number, nothing. And what I will do, I will try to quantify what amount of shear stress we are having at this point. So maybe this one is 7. Some arbitrary number 7 here, okay? And for this one, maybe it's 13 maybe, I don't know. Okay, so For dilatant fluid, there is another name for this one, which is shear thinning fluid. If I apply more force, like from 7 to 13, viscosity is increasing or decreasing? What do you think from this number? Shear stress increasing, so viscosity is, slope is increasing. That means viscosity is increasing. And when the viscosity is increasing, it will act like solid. Yes. Okay. Now the next one, if I use a different color here, this one, there is one slope here, one slope here. Give me one number for this point, any number, which is obviously greater than 5, 7, okay? Now what do you think? Number here, it will be less than 7 or greater than 7? It will be less than 7 because you are seeing the line is getting flatter, right? So maybe I will use 3. Every number is arbitrary here. Don't just think, okay, how I'm getting this number. Yes. Oh, yes, that's true. Yes, because like with extra force, it is act like more solid. So it should be shear. You are correct, actually. That should be shear thickening. Like shear is like more, it's getting more thicker. Thank you for that. Okay. Now let's work with this one. Now at this point and this point, give me any number greater than 13 here because it is greater than 13. What number I should write here? 25. Okay, and what number I should write here? It should be in between 7 and 13. Any number? 11. Okay. 11. Okay. So for this one, pseudoplastic or shear thinning, what is happening here? If shear stress is increasing, what is happening with the slope? Decreasing. That means viscosity is decreasing. And once the viscosity is decreasing, it will act like what? More liquid, right? And that's why it's called shear thinning, like it's getting thinner so that it can move very easily. And you already know one example of dilatant fluid. What is that? Water cornstarch. And for pseudoplastic, I will give you one example. Tomato ketchup. Have you seen when you open the tomato ketchup, like if you want to pour, sometimes it doesn't want to move, right? At first point, it's so stiff. It's like I don't want to move. But then if you tap on the back of that bottle, glass bottle, slowly it will start moving, right? So what you are doing actually, you are applying some force. So the viscosity is what? Decreasing. It is getting thinner, right? So the example of pseudoplastic will be what? Ketchup. Yes. Now, for your test or for any extra point question, if I just give you the characteristics, can you identify what type of fluid it is? It is Newtonian or not non-Newtonian? If it's non-Newtonian, it's shear thickening or shear thinning. Okay, so Even if you don't know at that point, you can always come back to class lecture 4, 5, and 6, and you can at least try to identify, right? You can at least try. That's what I want. Okay. Are we good up to this point? How many different types of fluids, like broad categories of fluid we can have based on the uh, viscosity? 3 broad categories. 2 Newtonian, non-Newtonian. Under non-Newtonian, how many categories we have? Again, 2. One is shear thickening and shear thinning. Shear thickening is with applying force, it is getting thicker. Shear thinning is with applied force, it is getting thinner. Even if you don't know the name, if you can just remember the examples, I'm sure you will have some sort of idea what we're talking about, right? Okay, good. There is one more type. These are two major types. There is one special type. It is called inviscid fluid. So inviscid fluid is when the viscosity is 0. Now, this is not possible to have a 0 viscosity because viscosity is the characteristics of the fluid. If there is no viscosity, that is not fluid. So this is not real, but for some fluid like water or air or oil, we can have a very low viscosity. So we usually consider those fluid as an inviscid fluid when the viscosity is very, very low. So I will make a note here that in real, inviscid equals to very low viscosity. Okay, all of these line, this is just some technical issues. I'm not crossing out anything here. Okay. Now, all of you should have your appendix A with you. Do you have that? Can you open that? And can you give me the viscosity of water at certain temperature and viscosity of air at certain temperature? Give me a viscosity of water at 20 degrees centigrade. And when I say viscosity, it's the dynamic viscosity, not the kinematic one. From appendix A, 1 times 10 to the power minus 2.
Minus 30.
Can you tell me the temperature? 20 or 25 degrees? 20? Okay. Okay. Now give me the viscosity of air at what temperature you have in your appendix A. I can't remember. Most probably 15 degrees centigrade or something. Okay, give the viscosity of air. -6 Newtons second per meter square at 15 degrees, right? Now, can you see these are very small numbers, 10 to the power -6, which is very small, and 10 to the power -3, that is small also. So, we can say, though the viscosity of water and air, they are not 0, but they are very small, and we can consider these fluids as inviscid fluid because their viscosity is very, very low here, very low viscosity. Okay. Now, there is another type of fluid which is called ideal fluid. So, ideal fluid is when it is inviscid Thus, incompressible. Do you remember what is the characteristic of incompressible fluid? What type of fluid we can call incompressible? Which is unable to, say it loudly, incompressible means what? Which is unable to compress. Yes, from the name we can say that it's unable to compress. So if any fluid is incompressible and inviscid, that time we can call that fluid as an ideal fluid. What can be the best example of ideal fluid? What is the best example of ideal fluid? You have one example on top of that. Water, yes. Okay. So in real, obviously, we can't have inviscid fluid. It has some sort of viscosity. That's why instead of ideal fluid, sometimes we refer as the real fluid. Real fluid means it has some sort of viscosity. It's incompressible. It's called the real fluid. Okay. Okay. So we have one more topic for viscosity. After that, if we have time, we will do one mathematical problem. If you don't have any time, that's okay. We will do that in next class. After that, we will have only one more basic property to cover, which is the surface tension. Once we are done with that, we are done with the basic properties. We can start the quiz. Okay. All of you are done with this one, this slide, back. Very good. Okay. Now, the next topic, the effect of temperature on viscosity. Just think about that. If you heat up the molasses or honey, what will happen? It will be more liquid or it will get more solid. It will be more liquid. That means for certain fluid, if you apply heat, it will get more liquid, right? If you look at the examples here, like the water, mercury, crude oil, with increasing temperature, viscosity is decreasing. But what about these? Air, carbon dioxide, hydrogen, their viscosity is increasing or decreasing? Which is little bit counterintuitive, right? We always thought if we apply temperature, it will loosen up the hard molecules bonding or something. So let's discuss why we are having different, it's like different case for gas. So for both cases, if you apply temperature, molecules, vibration or speed, what will happen? It will be increased or decreased with temperature. Increase. The same thing here, if you apply temperature, molecules vibration will get increased for both cases. Once molecule vibration gets increased, they will break down the intermolecular bond, right? So breakdown of intermolecular bonding. The same thing here. From back, can you read my handwriting? Or it's too small for you? And once there is a loosen of the bonding, molecular bonding, what will happen? There will be layers of liquid. Will loosen up, and that's why with temperature usually the viscosity gets decreased for liquid. Now, for gases, all the molecules, they are already spread out like all over the places, right? Now, if they get more speed, what will happen? They are already spread out. If they get more speed, there will be more collision, right? And more resistance. And that's why for gas, you apply temperature, the viscosity gets decreased. So what I will write down here, increased molecular speed will create more collision, which eventually increase resistance. Now, if I ask you for any quiz or test for gases, why with increasing temperature, viscosity increases? Can you explain? Maybe not in these words, but in your words so that I can understand what you are trying to say. Can you explain that? Or did you get the idea why with increasing temperature, viscosity is increasing for gases? You got that idea? Little bit? And for liquid, the viscosity will get what? It will be lower with increasing temperature. Good. So it's just a little bit different characteristics for gas and liquid. And that is the end of viscosity topic. After that, we will do some mathematical problems. But please ask me if you have any question or any confusion. I will be happy to answer any confusion or any concern you have. Do you want me to go through any topic again just to clarify or something? You're good, all of you? Okay. If you're good, I'm good. So for after that, we will start working on the class example 4. I gave you class example 4, I think in last class. Do you have that with you right now? Okay, open that. We have only 4 minutes. I think we can just start working on that and we will complete that in our next class. Can anyone read the class example 4 loudly so that everyone can hear?
0.15 meter wide plate has 2 layers, A and B. A oil that has a kinematic viscosity of 4.5 45 the rate of 5 liters squared per second, and density of 880 kilograms per meter cubed. Determine the force B required to move the plate at a constant speed of 6
millimeter per second.
meters per second. Neglect any friction at the end of supports. Assume the velocity profile to be
Thank you very much. So what they are saying here, they say that 0.15 wide plate. So we are seeing a 2D view here. If I try to draw a little bit 3D here, it should be something like that. So this dimension should be 1.5 meter, right? And we also know the length and everything. And we have 2 layers of oil here. One is layer A, one is layer B, and they are asking you to find the force P, right? Now we know some characteristics of the oil. We know the kinematic viscosity and the density. Now let's go to the next page and write down what we already know and what we need to find out. Okay. Now there are a few things. They said that neglect any friction at the end support. That means they are fixed. All the support here that is actually fixed here And they also say velocity profile through each layer is linear. So there is no parabolic velocity profile or something. Now, since this one is the fixed support, what do you think? What will be the velocity here? For fixed support, velocity will be? It's fixed, it's not moving, so velocity 0, yes. And at this point, at midpoint, do we know the velocity? Is it given on the question? What will be the velocity here? At this point, at which speed you are pulling the plate, is it given? 6 millimeter per second, perfect. So 6 millimeter per second. Now, if you have 0 and 6, obviously you can draw the velocity profile like these way. The same thing for this layer also. That is the velocity profile. Okay. So I will just stop here, and from next class we will identify what parameters are given and what we need to calculate. Okay. Please bring your class example 4 in next class, and please bring calculator. Okay. Thank you very much. I will see you on Wednesday.